to approximate area for more complicated curves, what we can do is use rectangles. So we're going to focus on two forms of estimating with rectangles. One's going to use the left endpoints and one's going to use the right endpoints. So it won't give us the exact area. Again, we're kind of building up to that, because to get the exact area, we're going to do some calculus. But in terms of geometry, we can do is get some estimations using these rectangles. So what we're going to do here is look at negative x squared plus 11. So let me go ahead and get a drawing going for us. So we'll have vertex up at 11, and then this is just our parabola opening downwards. Let's see, 3, 6, 9. 3, 6, 9. Okay, so our parabola is doing something like this. And what we want to do is look over the interval -1 to +3. So here's our cutoff at -1. Here's our cutoff at +3. And we want to find that area under the curve between those two cutoffs. So this is complicated since we have curvature to the parabola. So what we're going to do is use rectangles. So with this one, often we'll specify, so we're going to use 4 rectangles here. So what we need to do is we want these rectangles to have the same width to them. So if we just focus on the x-axis here, so from -1 to +3, what we can do is nicely divide this up into units of 1. We could have calculated this by taking 3 minus -1, so kind of seeing what's the distance of our interval, and then knowing that we want to divide it up by 4 rectangles. So we'd have 3 plus 1 over 4, which is 4 over 4, and that would give us our distance of 1 to use. So if we're covering a further distance and using a more complicated number of rectangles, then what we could do is use this formula here. You can see that formula is down here below. This change in x is you take b minus a, if that's your interval endpoints, divided by n, where n is the number of rectangles you have. Okay, so we have these kind of cutoffs. So I'm going to have are these rectangles here. So they aren't rectangles yet because they're kind of matching up with the curvature of the graph itself. So let's say we wanted to do this using the left side, using left-sided endpoints. So what that would mean is it helps to read from left to right. So our endpoints, we're going to use the height at x equals -1. That's going to be one of them. So what we'll do is use this -1 and then our output at -1, which is a +10. We'll also use the endpoint at 0. So at 0, 11 is going to be one of our coordinates that we use. And then we'll use at +1, which is 1, 10. And then we'll use the endpoint at +2, which is 2, 7. So we have our 4 rectangles and we're using the endpoints at x equals -1, 0, 1, and 2. Notice we're not using the endpoint at 3, even though it's in the interval. It's just the nature of using the left-sided. It's how we start at -1, and then in terms of endpoints, 3 would not be included. So let's talk about the areas of these rectangles. So what we're going to use is each of them have a width of 1, and the height is going to be based on the output. So we're going to have 1 times 1 being the width. The height for that first rectangle is going to be 10. And then we're going to go plus 1 times the height of the second triangle, which is at 11, plus 1 times that height at 10, plus 1 times that height at 7. So we're using the y coordinates of those 4 coordinates that we were focusing on. So let's see, 20, 31, 38 is the area that we're estimating. Something I can see here is that this is going to be an overestimation. This is going to go beyond the what we actually have graphed because we keep going outside of our graph there, but it's still an estimation. So let's talk about what if we wanted to do the right-sided. Sorry, this might get a little messy. Okay, let's say I want to do the right-sided. So for right-sided, what I would do is read across the interval from right to left. So with this one, we're going to start at +3, and that's going to make a height. So one of our coordinates is going to be this 3, 2. And then we have our coordinate 2, 7. That's going to make a height of a rectangle. We're going to use 1, 10. And we're going to use 0, 11. But in this case, we're not using x equals -1. By the nature of going from this right side, if we try to take a rectangle using -1 as the right side, it goes outside of our interval. We don't want to do that. So to stay within our interval, we wouldn't use that coordinate at -1. So for this one, our widths are still 1, so I'd go 1 times, and we have the height of 11, plus 1 times the height of 10, plus 1 times the height of 7, plus 1 times that height of 2. So let's see, 21, 28, 30. And this one stays underneath the curve quite a bit, so I would expect this to be an underestimate. But still, especially with both of these, we can get an idea of about what that area is under the curve, just using rectangles. So this kind of calculation is called a Riemann sum. What it does is it takes the sum of rectangles to approximate an area under the curve. So something we'll do is first find the width of those rectangles, just focusing on the x-axis and how we're dividing up our interval. And then the Riemann sum is this adding up of taking each width times the height. And the height of those rectangles is coming from a y-coordinate or a function output until we complete all of the rectangles we want to. If we're doing left rectangles or a left-hand sum, then we're using the left endpoints for the height of the rectangles. If it's a right-hand sum, we're using the right endpoints. Okay, so let's go through one more example with this where we'll do left and right. Let me kind of separate this up. So let's say I do a left-hand sum first, and then I'll do a right-hand sum. So left-hand sum for f of x equals 1 over x. So what we could do is we could make a table. You can graph to also have a visual, so 1 over x from 1 to 5. So 1 over x is our rational function. And we're looking from 1 to 5. So this gives me an idea of the area. And what we could do is, let's see if this is 1 and this is 5, and we are going to use 4 rectangles. So we're again going to have a width of 1, because 5 minus 1 over 4 is just going to be 1. So that's going to be the width, or that change in x. So what we're going to do is have cutoffs at 1, 2, 3, 4, and 5. So if we're using the left-hand sum, what I can do is just make a table of values, so like x and y. And if I'm using the left-hand sum, then I start on the left-hand side, so I'd start at 1, 2, 3, and 4, but I would not include 5. And then our y values is just plugging into 1 over x. So we would have 1 over 1, 1 over 2, 1 over 3, 1 over 4. So our left-hand sum here, we would take 1 times 1, plus 1 times a half, plus 1 times a third, plus 1 times a fourth, and add those up, which would be about 2.08. So for the right-hand sum, the graph would look exactly the same. So I'd have my rational function. I'm just making a quick sketch here. So we're starting at 1, ending at 5, and we have these cuts off at 2, 3, 4 as well. Now with the right-hand sum, we're going to look at 5, 4, 3, and 2 to make the 4 rectangles, but we don't want to include 1. So if I make my table of values, x and y, we're looking at 2, 3, 4, and 5. So we'd have outputs of a half, a third, a fourth, and a fifth. So for this right-hand sum, to take each width, which the width is 1, so we'd go 1 times a half, plus 1 times a third, plus 1 times a fourth, plus 1 times a fifth, which is about 1.28. So that's just to show you how to do this with a table of values, and just be careful of, if you're taking the left-hand sum, that you're starting at the beginning of the interval. And when you're doing a right-hand sum, it's kind of like you're starting at the end of the interval, but you're just kind of reading right to left.